Green hydrogen is often presented as a single breakthrough technology that will transform transportation, power generation, and heavy industry all at once. But that framing misses the real story. Green hydrogen is not one technology, and it is not one solution. It is a full industrial value chain, stretching from renewable electricity and water at the front end, through complex production, storage, and logistics systems, and finally into very specific end-use applications. Whether hydrogen succeeds or fails depends far less on headlines or lab efficiencies, and far more on how well these systems work together in the real world. At ReneEnergy, our focus is sustainability, systems thinking, and clean tech realism, and that means understanding hydrogen not as an idea but as infrastructure. Every green hydrogen project begins with fundamentals that are often underestimated: electricity, water, land, and permitting. Electrolysis only makes sense if large amounts of electricity are available at the right price and with sufficient reliability. In many regions, grid interconnection queues stretch for years, and renewable generation is often curtailed during peak production hours. These constraints are not side issues, they define project viability. Water, too, is frequently simplified in public discussions, but real projects must deal with sourcing, pretreatment, purity requirements, and discharge management. Sustainability starts here. If electricity is not truly low carbon, or if water use creates local stress, the climate case weakens immediately. Systems thinking reminds us that hydrogen plants are not isolated machines. They are industrial facilities embedded in real energy markets and environmental limits. Once power and water are secured, the value chain moves into electrolyzer manufacturing. This is where much of the public narrative concentrates, but the real challenges lie beyond efficiency numbers. Manufacturing scale, durability, serviceability, and integration with balance of plant systems matter far more over a project's lifetime. Companies like Nel ASA have focused heavily on industrializing electrolyzer production, emphasizing reliability and repeatability rather than experimental performance gains. From a systems perspective, electrolyzers are long-lived capital assets that must operate for decades. Stack degradation, maintenance cycles, and spare parts logistics directly affect hydrogen cost. From a sustainability lens, longer-lasting equipment reduces material use and life cycle emissions. Cleantech succeeds when it behaves like infrastructure, not a prototype. The hydrogen production stage itself reveals the first major systems trade-off. Some projects are designed for steady baseload operation using long-term power purchase agreements, while others aim to operate flexibly, following renewable output or electricity market prices. Baseload operation improves utilization but can expose projects to power price risk. Flexible operation can support grid stability and absorb curtailed renewables, but it increases operational complexity and equipment wear. Sustainability outcomes depend on these choices. A hydrogen plant that soaks up excess renewable power can strengthen the grid, while one that competes with local demand can raise costs elsewhere. Cleantech here is not just about producing hydrogen, but about producing it in a way that improves the broader energy system. After hydrogen is produced, it must be conditioned before it can be stored or delivered. Compression, purification, and sometimes liquefaction are among the most energy-intensive and capital-heavy parts of the value chain, yet they receive little public attention. Compressing hydrogen to 350 or 700 bar consumes significant electricity. Liquefying hydrogen consumes even more. These steps determine which markets hydrogen can realistically serve. Short-distance industrial users may accept compressed hydrogen, while long-distance logistics and centralized fueling often require liquid hydrogen, despite efficiency penalties. Sustainability demands honesty at this stage. Every conversion step adds cost and energy use, and those penalties must be justified by real operational value downstream. Storage is one of the most critical links in the hydrogen value chain, and often the difference between theory and practice. Hydrogen production and demand rarely align perfectly in time. Storage buffers that mismatch. Small systems rely on pressurized tanks or cryogenic vessels, while larger systems explore underground storage options such as salt caverns. Companies like Air Liquide bring decades of experience operating hydrogen storage and distribution infrastructure, including large-scale storage solutions integrated into industrial networks. From a systems perspective, storage provides resilience and operational flexibility. From a sustainability standpoint, it reduces waste, curtailment, and emergency venting. Cleantech that cannot store energy reliably is fragile. Transport and distribution are where many hydrogen projects encounter their hardest constraints. Hydrogen is expensive to move. Tube trailers carry limited payloads and are best suited for short distances. Liquid hydrogen trucks carry more energy but require cryogenic handling and suffer boil-off losses. Pipelines are efficient at scale but require massive upfront investment and long permitting timelines. Systems thinking forces a geographic question that cannot be avoided. Where is hydrogen produced? Where is it consumed? And how far must it travel? Sustainability requires accounting for emissions and energy use in transport, not just production. Cleantech viability depends on aligning supply chains with realistic demand clusters. Fueling and dispensing infrastructure is where hydrogen stops being an abstract commodity and becomes a service. For mobility and material handling applications, uptime, throughput, and safety matter more than theoretical cost per kilogram. This is where integrated approaches have proven most effective. Plug Power provides a clear example. Rather than selling fuel cells alone, Plug Power built end-to-end hydrogen ecosystems for warehouse customers, including on-site liquid hydrogen storage, vaporizers, compressors, and high-capacity dispensers. This systems-level integration reduced operational friction and enabled hydrogen adoption where piecemeal solutions struggled. Sustainability here is not just about emissions. It is about replacing inefficient operational patterns with reliable ones. Cleantech adoption accelerates when systems are turnkey. Understanding why hydrogen works in some applications and fails in others is essential. Hydrogen performs best where energy density, fast refueling, centralized infrastructure, and high utilization matter more than raw efficiency. It struggles where electricity can be delivered directly, cheaply, and with minimal friction. Material handling is a strong success case because forklifts operate continuously, refuel frequently, and return to centralized depots. Battery alternatives lose productivity during charging or swapping. Hydrogen forklifts refuel in minutes and maintain consistent output. This is not because hydrogen is more efficient than batteries, but because system-level economics favor uptime over efficiency. Industrial hydrogen use is another area where hydrogen works well. Refineries, chemical plants, ammonia facilities, and steel producers already consume large volumes of hydrogen, often produced from natural gas. In these cases, green hydrogen does not need to create a new market. It replaces an existing molecule. Infrastructure, safety practices, and operational expertise already exist. Financially, demand is stable and predictable. Systems integration is easier. Sustainability benefits are real when gray hydrogen is displaced. This is why industrial gas companies focus heavily on industrial hydrogen, rather than consumer hype. Hydrogen can also make sense for long-duration energy storage and backup power. Batteries excel at short-duration storage, but costs rise sharply as duration increases. Hydrogen, despite lower round-trip efficiency, can store large amounts of energy for long periods and convert it back to electricity when needed. In microgrids, remote facilities, and critical infrastructure, resilience matters more than efficiency. Systems here are designed for availability, not perfection. Sustainability depends on clean hydrogen sourcing, while Cleantech innovation focuses on durability and integration. Where hydrogen struggles is just as important. Passenger vehicles are a clear example. In most urban environments, electricity can be delivered directly to vehicles through existing grids, and charging can occur at home or work. Introducing hydrogen adds layers of complexity: production, compression, transport, storage, and fueling, without delivering proportional benefits. The result is higher costs, sparse infrastructure, and weak adoption. This is not a failure of hydrogen chemistry, but a mismatch between technology and use case. Hydrogen also struggles where infrastructure utilization is low. A hydrogen refueling station serving a small number of vehicles will always look uneconomic. Systems economics punish underused assets. Sustainability narratives often overlook this reality, but financial models do not. Viability depends on throughput, not potential. Logistics distance further compounds the issue. Hydrogen is costly to move, so projects that locate production close to demand perform better. This is why hydrogen hubs and industrial clusters matter and why isolated projects often fail. Electrolyzer economics reinforce this point. Electrolyzers are capital-intensive assets that perform best when utilized consistently. Regions with cheap, abundant renewable power and strong grid access enable high utilization. Regions with volatile power prices or constrained interconnection see electrolyzers sit idle, driving up costs. This is where financial modeling becomes essential, not as a spreadsheet exercise, but as a reality check on system design. Even if electrolyzers were free, hydrogen would still require power, water, compression, storage, transport, and customers. The bottlenecks are systemic, not technological. When hydrogen projects fail, it is rarely because the science does not work. It is because the system does not close financially. Power is too expensive, utilization is too low, infrastructure is underused, logistics are too long, or demand is uncertain. Sustainability goals cannot override these fundamentals. They must operate within them. This is why ReneEnergy approaches green hydrogen through a sustain, systems, and cleantech lens rather than treating it as a universal solution. Green hydrogen is not a silver bullet. It is a system solution. It works best when it replaces something inefficient, carbon-intensive, or operationally constrained. It fails when it competes head-to-head with direct electrification where electricity already excels. A mature energy transition will be diverse, not uniform. Batteries, electrons, molecules, and fuels will each play roles defined by physics, economics, and infrastructure. This is the perspective ReneEnergy exists to bring. We focus on how clean energy technologies actually function in the real world, across sustainability outcomes, system design, and clean tech execution. If you are developing, investing in, or evaluating hydrogen projects, understanding where hydrogen fits and where it does not is not a weakness. It is the foundation of responsible decision-making.